Ah, why? I can't see. It's just so close. Why is it so close? What happened? Ah. So it's stuck. Okay. All right. Okay. Well, good to see everybody. How are you doing? It's fabulous. I can see. I can tell. All right. So we have few more lectures and we'll be done. Um, the student rating of teaching, if you have not done it yet, please do. You have a +2 extra credit for doing that. I think we only have 5 more that didn't do it yet. If all of you, if I get 100%, so you get another +2 on the final. Wow. So instead of just +2 for doing it individually, if we get 100%, everybody will get +2. So it does really matter to me and to us as faculties to get those rating of teaching. Okay. So let's see. Do you remember what I was talking about before Wednesday? I started pH titratable acidity. You did a lab on it. And also you heard that you don't have a lab report, you. Wasn't that fantastic news? I don't hear the excitement. Maybe I should assign it. Okay. All right. So let's try to remember what I started or talked about last Monday. If two acids have the same concentration, do they always have the same pH? No. Very good. Why? Right? And they might not be a strong acid. Strong acid completely dissociate and lowers the pH much more than a weak acid that will not dissociate fully, so it won't lower the pH to the same level, even though it's at the same concentration. What does titratable acidity affect in a food? So what does it mostly impact? Titratable acidity or total acid? What's the one thing that it would affect the most? Yeah, flavor. So total acid will impact a flavor mostly. All right, what about pH? What would it impact? Affect. Yeah, so for what kind of reactions are impacted? Microbial, chemical, enzymatic. Very good. Thank you. Oh, let's remember your favorite topic. What's pKa? Hmm. Hmm?
Typically for both like 50% of our protein and 50% are not.
Yes. So it is the pH. Well done, well done. They got excited for you, they clapped. Okay, so it's the pH at which we have equal concentration of acid and conjugate base, or protonated and non-protonated. And it is the pH at maximum buffering capacity. So in lab, you did plot the buffering titration curve of malic acid to understand, and we're going to show you the titration curve here, that when we are around the pKa of one of the carboxyl groups, the pH resists change. It's a buffering zone. Okay. Can an organic acid buffer at multiple pH? Yes, why?
Because it can have multiple.
Yes, multiple carboxyl groups specifically. So for example, citric acid has 3 carboxyl groups. Lactic acid or acetic acid, they have 1 carboxyl group. So, yep. All right, let's continue where we left off. If this wants to, yeah, there we go. All right. So titratable acidity is the measure of the intrinsic acid in a food. So basically, the most dominant acid in the food. So like if it is milk, you want to measure titratable acidity of milk, it would be lactic acid. If it is orange juice, it would be vitamin C or ascorbic acid. If it is lemon, it could be citric acid and so on. Tartaric for grapes, malic for apple. Okay, citric, we also did 7-Up. You use citric acid as the main acid in 7-Up in lab. We do have inorganic acids. Phosphoric acid is commonly used in beverages. And carbonic acid is when carbon dioxide is dissolved in water, it forms carbonic acid. And it buffers around the endpoint. And that's why when you leave the lab, without boiling your 7-Up, you have the CO2 in there, you overshot the titration. So because carbonic acid and phosphoric acid, they actually buffer around the 8.2 range where your phenolphthalein indicator changes color. So in order to determine the endpoint, we either use a pH meter like you did in the lab and you stop titration when we reach pH 8.2, or we use an indicator and we stop titration when the color turns pink. All right, and this is your favorite equation of the whole wide world, which is the Henderson-Hasselbalch equation. Okay, so we need to understand the buffering principle is where we have the pKa, where the pH equal the pKa. So this concentration. So when the conjugate base concentration equal the acid concentration, then log will be 1. Log of 1 is 0, and then pH equal pKa. So, and this is just a reminder that all food acids are weak acid, they're organic acid, they have low dissociation, and therefore they have this buffering capacity. All right. So the equivalence point is when we have number of acid equivalents equal number of mole of base equivalents. So at equilibrium, number of moles of acid equal number of moles of base. So the reaction ends when all the acid is neutralized and the next drop of base turns your solution pink because of the phenolphthalein indicator. And as soon as you reach that point, you see a spike in pH. So you did that when you did the apple and pH meter, apple juice and pH meter. So as soon as we deplete all of the HAs, you see a real high spike of pH. So this would show as soon as all the acid is neutralized, you would see sharp increase, and you would extrapolate at pH 8.2 the amount of NaOH used. And that's what you did in the lab for the malic acid. And here we're showing different titration curves. This is a regular titration curve for just HCl, where you don't see a buffering zone. It just keeps increasing until all acid is neutralized. here this is citric acid. So you have three carboxyl groups. So you would have three pKa values. For every carboxyl group, you'll have a pKa, which is a dissociation factor of this H in the carboxyl group. So you see three buffering zones. So you see an increase in pH, and then there's a buffering zone around the first pKa, then the pH increases, another buffering zone, and a third buffering zone until all H's have been dissociated. And then we see a spike in the pH. This here for acetic acid, so which has only one pKa, so we see only one buffering zone. And you already plotted titration curves, so you already are experts in that. All right, so let's determine the percent of lactic acid that is dissociated and present as a conjugate base when the acid is dissociated, so it will be A minus or conjugate base. What percent of that lactic acid will be in a dissociated state when the pH is 4.7, and we know that the pKa lactic acid 3.86. So please take out a piece of paper. We're going to do quite a few calculations and start doing the math. So here you need to apply which equation? Your favorite. What is it, Golden? Yeah? What is it? pH equals. Yeah. All right. And then you have to remember that give you a hint here. So in a solution that is made up of conjugate base and it's acid, you have assume, where's the light? Okay. So you have to assume that HA plus A minus equals 1. So the two parts equal a whole. So this is an assumption that you can use in addition to your equation. What do you get? One close. If you guys get stuck on somewhere, on something. So what's the pH? 4, 4.6, 7. What's the pKa? 3.86. 3.86. If I want to solve for A minus, the percentage of A minus. So I would want to replace HA. If I want to replace HA, what do I put instead of HA? Yes. So A minus equal 1 minus 1. There. So now, can you solve for the ratio? What would that be? Using your calculator and inverse log. Huh? 3.6. No. So, okay. So 4.7 minus 3.86 equal log A minus over 1 minus A minus. So what is this value here? 0.94? 84. Okay, so what is your calculator telling you? The log 0.84, so the inverse of that. I just want to get this. If I have log of this equals 0.84, what would be the ratio? On your calculator. Isn't it like inverse log something? What? You don't have a calculator that gives you that value? Huh? 6.92. Yeah. You got 6.92? What did I hear?
I don't know.
I didn't hear 6.92. Oh, you were just, I didn't hear, yes, it is 6.92. Sorry, I heard 3 point something. Okay, sorry, I confused you. Okay, now tell me what A minus is, the concentration. Solve for A minus, huh?
0.87.
0.87, what would be the percentage? The percentage would be 87%. 87% of the whole. There you go. 6.92. I don't know what I heard. Anybody lost in the calculations? Okay. So what you need to remember is the acid and base represent the whole. So it's always 1 or 100%, right? So, and we are determining the percentage that is dissociated at this pH. Okay. All right. So basically, titration, we can use a pH meter during titration like we did in the lab, or use an indicator that will change color around pH 8.2. Why it's pH 8.2, not 7, the neutralization pH? I think we mentioned it briefly last time. Why neutralization, or I didn't, or maybe in the lab. Why neutralization is not pH 7, it's 8.2? Because the dissociated base, it is a conjugate base. So usually it has a little bit higher pH than 7. So that's why the end point, when all of your acid is dissociated, it will be a little higher than pH 7. It will be around pH 8.2. And it so happens that this pH is in the range of phenolphthalein changing color. And that's why we can, once phenolphthalein turns pink, then that's the end of the titration. And the good thing is with food acids, they don't buffer at pH 8.2. However, phosphoric acid that is added and carbonic acid that forms in the presence of CO2 and water forms carbonic, that's why you overshot your titration in lab when you did not boil off the CO2, because it buffers around that pH. So every time you reach the end point, it buffers, and then you continue adding, so you overshoot. So in this case, you can stop titration using pH meter, and once you reach 8.2, you stop titration instead of having to having the indicator color being disappear over time because of the buffering zone. Sometimes also if you are titrating tomato juice, yes.
With phosphoric acid, carbonic acid, could you also, instead of using the pH meter, could you also just boil it like we did? Get rid of the carbonic acid, or as well as sodium acid?
Well, then if you boil it and get rid of the carbonic acid, you can determine how much carbonic acid you had if you really want to determine carbonic acid.
But what if you don't want to determine the carbonic acid?
Then you don't care, you determine another acid. So it really depends what you're trying to determine, which acid. Okay. And then if you have a sample like tomato juice, you want to determine total acidity of that, you cannot see a color change, then you would need to use a pH meter. All right, and then in the lab, we have prepared boiled water for you, and we put an Esker trap. Have you seen it? Did you see it in the lab? Okay, so it's basically, we had kind of a syringe like filled with silica, and the silica is coated with NOH because then it can trap any CO2 residual in the headspace and react and form this sodium carbonate. Because this is important so that we can continue to make sure that we don't have CO2 in your water. And then NOH that you use for titration, you did standardize as well, because when you prepare NOH and you leave it for a little while, the NOH will react with CO2 dissolved in water or in the environment above it and form sodium carbonate and reduce the normality of your reagent. So it's very important to standardize your NaOH solution using a standard acid, and what you used in the lab is the potassium acid phthalate standard that you use to standardize your NaOH, and then you standardized HCl, and that HCl usually we use for titration. For example, CalDOT, it has to be standardized so that you calculate the exact normality to use in your equation to have more accurate results. All right, and then at equilibrium, it's percent titratable acidity. So it is weight by weight. So it's the same derivation of the equation at equilibrium. The only difference is instead of having just the molecular weight, we need to make sure it is the equivalent weight because some acids have more than one hydrogen in the equation. So we have to take into account the equivalent weight, which is really the molecular weight divided by the number of equivalents. So how many hydrogens do we have that can be part of this equation? So for example, in the lab, you took the citric acid molecular weight and you divided it by 3 because it has 3 carboxyl groups, so 3 hydrogens that take part in the equilibrium of the equation or the reaction. So that's why it's equivalent weight. Malic acid, you took the molecular weight and you divided it by 2 because you have carboxyl group. So in any question in exam I give you, I will tell you how many carboxyl groups you have so that you can determine the equivalence weight. So I give you the molecular weight of citric acid, and then I will tell you we have 3 pKa's, meaning you have 3 carboxyl groups. So I'll give you that so that you're able to determine or calculate your titratable acidity, which you can go ahead now on that same piece of paper. Okay. Should be easy. Just apply the equation. What's the equivalent weight of citric acid? 64. All right. So you have everything else you need. You divide by the volume of the sample and multiply by 100. So you will get percentage of grams per 100 milliliters. So what do you get? This is the equation, right? So normality by the volume of the titration, we divide by 1,000 because the volume is in milliliter and you need to convert it to liter for the equivalence times 100. And the weight, it can be the volume that was given to you, which is 15 ml. So what do we get? Yep, which is 0.6%. All right, just applying the equation, the only thing you have to really remember is that you use the equivalent weight. based on the number of carboxyl groups. Instead of the molecular weight, use the equivalent weight, because if you have more than one carboxyl group, you have multiple hydrogens, multiple number of equivalents. Okay, and this is FYI, so you have to know that organic acid percentages is usually low in the different foods. So it's like probably from the highest here you can see is probably lemons have highest acidity with lemons and lime, but mostly everything is almost one or under. So just to keep that in mind and keep things in perspective, the titrative acidity is usually low. So, and like we said earlier, the titrative acidity is determined based on the predominant acid. There might be more than one organic acid in your food or juice, but we calculate it based on the most predominant acid. The Brix to acid ratio is predictor of acid flavor and also maturity. And then volatile acidity is a test used to determine how much vinegar ended up being in wine, which is a quality parameter. So in order to determine the quality of wine, you would measure titratable acidity as is. Then you boil to kind of evaporate acetic acid if it's there and measure titratable acidity after that. And then you will determine how much vinegar you had in your wine. This is not a good thing. All right, so this was the lab, and then I'm going to move on to minerals. You covered vitamins on Wednesday with Dr. Gallagher. I'm going to continue with mineral analysis. Off every time. Okay. No. All right. Why is it important to analyze minerals? Specific minerals. Your favorite, huh? What? Nutrition label. Nutrition label is one. What else? Huh? How do minerals impact perishability? Metals can cause oxidation, yeah. Okay, good. Yes. I didn't have that as one of my points, but yes. What else you can think of? Do you know the difference between fortification and enrichment? Ah, what is the difference?
Adding something that hasn't been in it.
Yeah.
And then enrichment is adding something that was really put in processing.
Exactly. Like, can you give an example?
Yeah, like processing of wheat, you can add that in like vitamins lost in one gram.
Yes. Very good. Very good. Yay. Amazing.
I like minerals in that.
Good. Good. So yes, fortification is, let's say, adding calcium to your orange juice. So that's fortification. Or adding some vitamins and, well, some minerals, because this is minerals we're talking about, to cereal. And then you'll see on the box of cereal all the minerals that were added, fortified. Enrichment is when we lose something during processing, like a white flour. So it is debrand, and then you lost zinc, you lost iron, you lost some vitamins, but mostly in this case, because we're talking about minerals, we have lost iron, so you have to enrich to the starting iron concentration of whole flour. So that's called enrichment. And then there is oh, what minerals are on the label? Yes. iron. What else? Calcium. Huh? Iron and calcium and
Potassium.
potassium and
Sodium.
sodium. There. All right, so we have the calcium, iron, we have the sodium, and well, this is the new one. Calcium, iron, potassium, and sodium. Yes. So for nutrition labeling, we talked about fortification and enrichment, processing effect that will cause us to lose some minerals, but also, do we add minerals during processing for a specific effect? What kind of minerals we add during processing that have some importance and we add them for a particular performance?
Bread.
Calcium help with bread?
So something.
Calcium help with something.
Yeah.
So calcium helps with producing curd, higher yield of curd. So we add calcium to milk. We also add calcium when we're making tofu, helps with gelling of the protein. So yeah, that salt sometimes you add for not only for flavor, but also during fermentation to suppress certain growth and induce other types of growth. So salt is added. So minerals are important for some functionality, for flavor, for preservation. So they're important. Water quality. What do we normally measure? When you hear water quality, what would come to mind? Water hardness. So water hardness is due to presence of calcium and magnesium usually. So hard water, so it will be high in calcium and magnesium. And hard water sometimes is not really good because let's say you're trying to make pickles and you put water that has a lot of calcium and magnesium. What's going to happen to the water in your cucumber? Yeah. So it's gonna go out, it's causing it to shrink. So hard water is not always the best to use during processing because it can impact the structure of the food by causing, water movement by osmosis. Okay, so we do measure water quality by determining calcium and magnesium in water to determine whether it's hard water or not, or the hardness of water. And we determine minerals for nutrition labeling and for claims of fortification or enrichment. So minerals are classified into macro elements that are needed in higher amounts than trace elements that are needed, but in much smaller amounts. But then there are also the toxic elements that should not be present in foods we eat. Okay. So we already studied atomic absorption or emission, and a lot of the minerals are really determined using atomic absorption spectroscopy or inductively coupled plasma atomic emission spectroscopy, which we already studied. Today, I'm going to talk about a few other ways of measuring mineral content for when you're measuring one specific element or mineral and in a small set of sample. So you don't need to use AA, you don't have AA or ICP, so you tend to do other ways of analysis. We're going to talk about examples of titration, colorimetric assay, and ion selective electrodes. So these are the different types of assays. In particular, titration does not necessarily require pre-ashing. However, if we want to determine by atomic absorption or ICP, we need obviously to ash the sample, which we did, for example, for the atomic absorption lab. If we want to do colorimetric assay, we need to get rid of the organic matter and interfering substances. So yes, we ash. And for ion selective electrode, we also most of the time require ashing. So during sample preparation, there are several considerations. The most important consideration for sample preparation is what? You want to avoid what? Mineral loss, yes, but another one that you want to avoid, contamination. So you want to avoid possible contamination. So we always run a blank, but also we wash the all of the utensils acid wash, so we don't have any previous minerals coming from not coming from your sample. Okay, interferences. So sometimes your mineral become ionized depending on the pH and temperature. Sometimes if you're doing colorimetry, there will be interfering substances. And then reagents might carry contaminants. So what we do is we always prepare standards and blank, and we prepare the standards the same way we prepare our samples. So these are different ways we really need to consider as we prepare samples for mineral analysis. Okay, let's talk about complexometric titration. From the name, so you have EDTA, it forms a complex with the elements. So EDTA is a metal chelator, right? It chelates metallic forms of the mineral. So for example, for hard water, EDTA can bind to calcium and magnesium. So if I want to determine the hardness of the water, so I get my water sample, I add to it an indicator, Palmagite. A very annoying name, but this indicator, once it binds to the ionic form of the metal of interest, calcium or magnesium, it changes color. So its color is blue, it becomes pink. So now you have your water that is pink in color because of that indicator. Then you titrate with EDTA. The EDTA binds the ion more strongly than the indicator. So when you're titrating, so the indicator is displaced and the calcium or magnesium will bind to the EDTA. And then you keep titrating until all of the metal in your water, calcium or magnesium, is now bound to EDTA. Then your indicator will change color back to blue. Okay, so the concept is simple. You put the water, you have the indicator, it changes from blue to pink because it bound you that metal. Then you titrate. EDTA will displace the indicator and bind to the calcium or magnesium. Keep titrating until all the indicator has been freed, so no longer any ion attached to it, then it changes back its color to blue. And that's the end of your titration. A consideration here is that you want to make sure that you titrate under alkaline conditions because EDTA can be easily protonated at lower pH. So if it's protonated, if it has the H plus in it, it won't bind to a metallic form of ion of your metal. So you want to make sure that it is alkaline pH so that the EDTA remains negatively charged so it can bind to calcium and magnesium. All right, that's the pH dependency here. Okay, so this titration, there are test strips. So it's easier to just test the water hardness by using the test strips and monitoring the change in color. So the test strips is impregnated with the reagents that are needed in the reaction. So these test strips are called aqua check test strip. Very easy. You can, based on the color, you can determine the degree of hardness. More titration is a specific titration to determine salt, NaCl. And we call it forward titration because it's simple. You just titrate with silver with excess silver nitrate, I believe. Yeah, so silver nitrate is the titrant, and you use an indicator, chromate indicator. So you titrate until you form silver chloride, and the last drop where all the chlorides have been taken up, then the silver will react with the indicator and give you an orange precipitate. Very simple forward reaction, and it also has test strips that you can use to determine the concentration of salt. So Vollard titration is a backward titration for salt. Now you would say we have an easy titration, which is forward. Why do we want to do the backward? I don't know. They just had this developed, the backward titration. Maybe it was earlier than discovery of doing it just straightforward, do the more titration. So in Vollard titration, so you add excess amount of silver nitrate. So you don't titrate with silver nitrate. You get your sample that has sodium chloride in it. You just add a known amount of silver nitrate to the sample in an excess amount. Then you take that and titrate with thiocyanate until all of the silver is picked up by the cyanate. And then the next drop of your titrant in the presence of an indicator, ferric ion, will give you a red color. And that would be the end of titration. So basically you put excess of silver nitrate in your solution, and then you titrate with thiocyanate to an endpoint that is red in the presence of ferric ion as an indicator. So time. Okay, so precipitation, titration, I'm finishing this slide. This is just saying that there are test strip based on more titration for salt. It's official method of analysis with good accuracy. All right, you want to go home? Yes.
Baby photo Kahoot.
Oh, yes. Do you want to do that on Wednesday?
Email photos to me of them as a baby. And then, no, Ali and I will be hosts.
Okay.
And then we'll make a Kahoot
Yes.
and everyone can play.
What's the prize?
Extra points. No.
No, so I'll get a prize. I'll get a prize. Whoever wins the most predictions will get that prize. Should we have first, second, and third place? Can you email me so I remember to do that on Wednesday? All right. Yeah, we'll do it in the last lecture on Wednesday.
Oh yeah, wait, everyone listen to Ali's joke.
Oh, you have a joke, yes.
What did sodium say to potassium when potassium asked it to go out? Nah.
Oh, an A now. All right.
The symbol for sodium is Na. Nah.
Oh, who didn't get it?
No, I said it sarcastically. Yeah. No.
Hello.
Oh my god, there's so much. I'm gonna do everything.